In this video, what I want to do is I want to describe an algorithm for computing the greatest common divisor between two numbers. And this is an algorithm due to Euclid. So this is therefore called the Euclidean algorithm or Euclid's algorithm. And what this is going to do is this is a very quick, efficient way of computing the greatest common divisor of two integers given the two integers. So we're going to start with two integers a and b, and we're going to use this algorithm over and over. Before we can actually describe the algorithm, I want to explain how it works via a proposition. And the proposition is the following. So suppose I have two integers a and b, and suppose that a is equal to bq plus r. And actually, we don't even have to assume. What we're going to do is we're going to take the larger number and divide it by b, and then use the fact that the remainder has to be between 0 and b minus 1. But this statement's actually true regardless of whether or not I've written a equals bq plus r according to the division algorithm. But say we have two integers a and b, and you can write a as bq plus r. So r is allowed to be whatever you want, q is allowed to be whatever you want. So if that's the case, then it turns out that the greatest common divisor of a and b is equal to the greatest common divisor of b and r. And before we get into a proof, let's talk about just an example. Let's say I have 300 is, let's say, 130 times 2 plus, let's see, that's 260, so we still need a 40 here. And so what this is saying is that the greatest common divisor of 300 and 130 is the same as the greatest common divisor of 130 and 40. Okay, it's 10 in both cases, but this is true. So the greatest common divisor of 300 and 130 is equal to the greatest common divisor of 130 and 40. So that's, again, just an example. Maybe I'll move that to the very end here. But let's prove the proposition, and then after that we can describe the algorithm, and then after that we can do an example or two. So our proof, and this is a proof of the proposition. Our proof of the proposition is, suppose that a is equal to bq plus r. What we're going to show, so we will show that the set of all common divisors, so the set of all common divisors of a and b is the same as the set of all common divisors of b and r. In particular, the greatest of these common divisors will be equal, because the common divisors are actually going to themselves be equal. So I'll go through and again, maybe I think it's best just to explain this in some detail. But if I were to look at, say, 300 and 130, and I were to look at what are the common divisors, what numbers do these have in common that they're going to divide them, it's going to be 1, 2, 5, and 10. It turns out that those are the common divisors of 300 and 130. And likewise, if I look at 130 and 40, what are the common divisors of 130 and 40? Well, the common divisors are going to be 1, 2, 5, and 10. So the set of common divisors are the same for both pairs. In particular, the greatest common divisors are equal. That's really what we're saying, and that's how this is going to work. So what we have to do is we're going to first suppose that D divides A and D divides B. And what we need to do is we need to show that D divides R, because then we would take a common divisor of A and B and turn it into a common divisor of B and R. Okay, so we want to show that D divides R. Well, this is true because if you remember, one of the things that I harped on when we talked about division is that if you have a common divisor of A and B, then so if D is a common divisor of A and B, then D divides every linear combination of A and B. In particular, D divides A minus BQ, since D divides AX plus BY for all integers X and Y. Right, so in particular, if X is 1 and Y is negative Q, then this is true. And from that, we get that D divides R. So that's already half the proof, because what this says is that if you have a common divisor of A and B, that's also a common divisor of B and R. On the other hand, if D divides B and D divides R, then we want to show that D divides A. The reason for that is, again, because if D divides B and D divides R, then D divides every linear combination of B and R. So again, by the same reasoning, D divides BQ plus R. So in this case, the linear combination of B and R that we're looking for is BQ plus R. Hence, D divides A. So this is enough. This is our proof. One thing that I think is helpful with this proof, which I should have included in the actual proof, is a little bit of notation. Let's say SAB is the set of common divisors of A and B. And likewise, SBR is the set of common divisors of B and R. So SBR is the set of common divisors of B and R. What we just showed, and basically our proof technique, was to show that these are two equal sets. So in particular, they're both subsets of each other. That's essentially what we just did. To show that SAB is a subset of SBR, you pick an arbitrary element in the first set, call it D. And to be in the first set means that you're a common divisor of A and B. And then you want to show that you're also in the second set. And hence, so we pick D in SAB, show that it's also in the second set. Likewise, you pick some arbitrary element, say D, in this set SBR, and then show that, well, that forces D to be in the set SAB. So you get that they're both subsets of each other, therefore they're both equal. Okay, so that's basically what we did there.